Okay, so this video is prepping you for the first part of our post-test in the fall semester of PreCalc for 2018. So this is the very first part of the post-test, or slow, sometimes we call it, and you have to kind of hop around because not all the questions, they don't go in order basically. So for instance, number 1, this is actually from the second part of the test. So we're going to skip that question for now, and that'll be on a different video. Same thing here with number 2. This is from part 2 of the test. So we'll come back to that in another video. Same thing with number 3. This is on part 2 of the test. Let's see, maybe we'll get one day. There we go. Number 4, yeah, this is on part 1. So this is a question that we'll be doing today on the first day of testing. So we'll mark that with part 1. So it says use the expression f of x to find the value for f of 0. So that's an easy question for you guys. You just need to plug in x equals 0. That's what that means. So you can either do this in your home screen, you could type it in y equals into your table. But let's see, I think I already did this one and I got 270 for my answer. And then use your calculator to estimate or to calculate the local maximum point, an xy ordered pair rounded to the nearest hundredth. So because of the follow-up questions here, I would say go ahead and use your y equals screen, your y1, type this into y1. And to find your local maximum, remember you go to second trace. And then you're going to go to maximum. And I'm going to pause my video so I can get everything entered. I would like you to do the same. So if memory serves me correct, this function is very strange. So it's a 4th degree polynomial. It's got a negative coefficient, so it's like an upside down, like, well, it looks like an M kind of. But if you just look at it in the home screen, you're not going to see a whole lot. So this particular function, the maximum is super high. So you could try to zoom fit. Sometimes zoom fit works, sometimes it doesn't. And this is a case where it really didn't work. So it's for some reason giving you very low points because of the way we had our x's defined. So what I'm going to do is I'm going to pull back. I don't really care to go negative, whatever that is, 22,000. Negative 10 would be fine. And then for your maximum, looks like we're going to need to go higher than 864. Let's just make it an even 1,000. Now when I hit graph, I should see a little better picture. Or maybe not. I should have gone lower in the y's. My bad. So let's go to like negative 100. Don't want it that skewed. Here we go. Okay, so something weird is happening on this function right here at x equals 3. Remember how the factor was x minus 3 to the 3rd power? So there was some multiplicity where it just kind of like snuck around and hung out at x equals 3 and then eventually crossed through. So we're not going to consider these to be maximums or minimums because it just kind of flattens out and almost appears horizontal at this point. But this guy right here, that's the maximum that you're going to need to find. So you do that by going to second trace and then going to maximum, number 4. And then when it says left bound, they just need a value that you know is to the left of the maximum. So something before the maximum occurred would be x equals, I'm going to go like negative 5 just to be safe. Okay, and then right bound, I'm going to go to like negative 1. That would be after it. And then guess, hit enter one more time. So the ordered pair, and it does say to round to the nearest hundredth. That first x value is just going to round up to negative 3.00. And then your y value won't need any rounding. It's 8.64. So if for some reason the function on your test isn't so pretty, well, not that that one was pretty, but it doesn't need any rounding, you can just write it like an integer like that. But if it does need rounding, make sure you go to the nearest hundredth. So then it says identify where it is increasing. This is a little confusing on this function because of the way the function looks. So this function is increasing on like this component of it right here. And then when it hits this peak, it switches to a decreasing function. And we're going to claim that it decreases for the rest of its domain. So the function is increasing starting at negative infinity. And then when it hits negative 3, it's going to switch over to decreasing once it gets over that maximum. So that was a little confusing on that question because of that weird multiplicity thing. I do not believe it is that strange on your test. Yeah, you'll be all right on your test. It's pretty obvious. But do watch out for more than one interval for where it's increasing or decreasing, because we've seen that happen quite a bit, especially on our polynomials. Okay, this next question, number 5, is, whoops, wrong page, Abruzzo. This is on part 2, so we'll save this for our next video. And then we'll skip to number 6 and 7 are also on part 2. So if you're looking for those questions, you gotta go find the other video. Or at least wait for it to be posted. Alright, number 8, this is on part 1. Alright, so we'll be looking at this one. And it says, describe, tell me all the zeros and describe any multiplicity, and then also describe the end behavior. So the zeros in the multiplicity are something that we can see from the function. So since it's in factored form, you can see that you have a 0 at 0, you have another 0 at 2, and then you have another 0 at -8. But the one with -8, since it has a third power, it has multiplicity 3. The ones that have multiplicity 1, you don't have to indicate those. For me, I'm okay with that. You have to check with Mrs. Hoffbauer to see what she wants if you're one of her students. And then for end behavior, you need a sketch or a mental sketch of what this looks like. So you have a 3, 4, 5th degree with a positive coefficient. So that would be like a cousin of the cubic with positive coefficients, so your end behavior looks like that. So the proper notation says f of x approaches -infinity as x's go to the left, and your function approaches positive infinity as your x's go to the right. So you need either a sketch or a mental sketch before you can come up with end behavior. Alright, number 9 is on part 1, so we're going to be visiting number 9 here in this video. And it says to your choice of method, divide these two functions with any method you want, and they just want you to give the quotient and ignore any remainder. So, of course, we're all going to choose synthetic because it's awesome. So -4 is what goes in the synthetic box. It's the solution to your divisor. And then do watch out for any missing terms. This time we don't have any missing terms, but on the test I caught a few of you with that mistake. 1, -6, 4, and -2. Alright, bringing down our first coefficient, and then it's a series of multiplies and adds. So that's a, what, -4, and then when you add those up, you got -10, and then -10 times -4 is positive 40, and when you add those up, you get 44. And because it said to ignore the remainder, you actually could get away with stopping here. What am I doing? You can get away with stopping here because your next step is going to be to find the remainder. It's, what is this, -176, I think. So this is -178, but because that's the remainder and they said to ignore the remainder, I'm not going to worry about that part, but I do need to apply some variables to these coefficients. So you started with an x to the third and you divided by an x to the first. So what that tells me is that your lead-off coefficient is going to be an x to the second. So we have 1x squared minus 10x plus 44 as a constant, ignoring the remainder. So that wasn't too bad. This is a theorem about possible real zeros and then number of turning points. So the number of real zeros that are possible is equal to the degree. So the degree on this question is a 4. And then turning points would be whatever the degree number is, but 1 less than that. So for us, that would be a 3. Should be some easy points on your test, right? Oh, I forgot to mark that that was part 1 of the test. That is definitely on part 1. Alright, so this question is also on part 1. It's on the next page. And we're going to be asked to factor this, so I go back to my factoring roots and I look for any common factors first. There's a common x squared that you could take out of here. And when you take out a common x squared, you still have x squared minus 4x minus 5. Now you're not done factoring because that trinomial I wrote in black factors again. So the x, well, f of x is the name of this, but x squared was out in front. And then if you continue factoring x squared minus 4x minus 5, that would factor into x minus 5 times x plus 1. So that's your complete factorization, and then it says find the real zeros, which means you're going to solve each of these factors. So like solving this one, you're going to get x equals 0. It does have multiplicity too, but you don't need to signify it here. And then this one would give you x equals 5. And then this one would give you x equals -1. So, not too bad. This question is a fun one. You guys love this question, don't you? Well, good news, it's on part 2. So, you get another day of thinking about how to find k on that question. Alright, this is on part 1 of your test, the possible rational roots. So what you do is you look at the coefficients, the leadoff coefficient, and then the constant part of the coefficient. And the rational root theorem is positive and negative, and then first all the factors of your constant. So don't worry about the sign there, just the 4. So your factors of 4 are 1 and 2 and 4. And then in the denominator of that possible list is all the factors of 3, so 1 and 3. And then you're supposed to write out all the possible combinations of these fractions. So I kind of cheat and just put plus or minus in front. I think if you're in Mrs. Hoffbar's class, she likes when you write them in front of each number. So first, if I divide all these by a 1, I get 1, 2, and 4. And then if I divide all these numbers by a 3, I get 1/3, 2/3, and 4/3. So that's our possible list, which is good because in the next question, which is also on part 1, it's the same function. However, this time they want you to figure out which of those rational roots are actual roots. So for most people, they go to their calculator and they look. So this particular example is kind of fun because it appears like you can see all 3 roots, but you won't be able to confirm them unless you actually confirm them. So like what I usually do is I write a little question mark to myself, and when I looked at my picture, it was looking like -2 and some weird fraction here that was between 0 and 1. So out of my possible root list that we just looked at, a -1/3 or 2/3 is probably the right answer, but I wasn't sure, so I kind of wrote down like -1/3 with a question mark, and then I wrote down a +2. I was really darn certain that 2 and -2 were zeros. So when I go to confirm them, we use synthetic division, and I just started with +2 because it seemed like easy math. I'm going to set up synthetic here. And then, if I get a remainder of 0, that confirms it for me. So, what do we have here? 6, 7, 14, 2... Oh, yep. So there's the confirmation. And then, this quadratic, you could either continue with what you think are the roots, or you could just go ahead and try to solve it, because it's a quadratic now. So that's usually what I do. Once I bring it down to a quadratic, I kind of stop doing the synthetic division business, and I just solve it. Turns out this one factors really beautifully. Also turns out that -1/3 was our other solution. So this factors into 3x plus 1 times x plus 2. So if you solved each of these factors, you get, what do you know, -1/3, -2, and then don't forget the first synthetic division is your other rational root that you used, and you confirmed. So for the explanation, you need to give me some words here about, using my list of rational roots along with my calculator, I think there's a rational root at 2, so then I did synthetic division. So this has to be filled out really, really well on your test, please. Now for factored form, sometimes you run into trouble when you, oops, it already says f of x, when you lose your lead coefficient. So make sure that since your original problem has a lead coefficient of 3, that your factored version does as well. What I usually do is I just drop these factors down from the quadratic, because those already were factored. And then the other thing I'm going to need to add into the mix was this solution at 2, because his factor was x minus 2. So that's a great answer. The other thing sometimes that kids will do is they'll take the roots and they'll write them like this. So they'll be like x plus 1/3, x plus 2, and x minus 2. But the trouble with that method is you lost your coefficient at some point. So the coefficient here was lost because of the division, so you need to kind of sneak it back in there. So either one of these answers is really great. I don't really care what method you want to approach it with. Alright. So we need to find all vertical asymptotes. So remember, your vertical asymptote rule is where you set your denominator equal to 0 once you've looked for any removable discontinuities or holes. Now there's no factoring happening on the numerator, so there won't be any holes. We don't have to worry about that. So if you just go ahead and set your denominator equal to 0, and you're going to find out that x equals both positive and -1. So your vertical asymptotes, there's two of them, and you need to write them as equations because they are lines. So x equals positive 1 and x equals negative 1. I believe there's something on your formula packet that you get that has all those rational graphing hints, and I think vertical asymptotes is a couple down the list, but you'll see it. It's the same one that we used on our original test. Alright, end behavior functions are referring to either horizontal asymptotes or oblique asymptotes. So horizontal asymptotes would be if you have, we talked about the top heavy, bottom heavy, or equal weight comparison. So here clearly we have a top heavy rational expression. So we need to realize that that means we have an oblique asymptote. So we have to find the equation of the oblique asymptote by finding the quotient of the division. And most of you love to set up synthetic division. I do too. So we're going to set up synthetic division by dividing, remember it's the solution to that denominator, so negative 3. And then watch here because you do have a missing term. You have a 4x to the third, a minus 3x squared, but you have no x's before the 4. Oops, I didn't leave myself a lot of room, did I? Alright, here we go, a bunch of multiplies and adds, and you don't have to worry about the remainder for the oblique asymptote. So you have negative 12, and then add those up and you get negative 15. And then we have 45. So then we have positive 45. And then I'm not even going to bother to do that step because I don't care what the remainder is. But you do have to remember that the end behavior equation means that it's the equation. You can either say f of x or you can say y equals 4x squared, because we're doing x to the third by x divided by x. 4x squared minus 15x and then a plus 45. So you will not get full credit if you don't write that as an equation. And then explanation using the end behavior rules has to do with, you don't have to use any official words here, guys. If you write things that make sense to me, that works too. So this was a top-heavy rational. So the quotient is the equation of the oblique asymptote. So remember the other options are if it's equal weight, that means the horizontal asymptote would be the coefficients of the lead terms, and if it's a bottom heavy rational, that means the end behavior equation would be the horizontal asymptote at y equals 0. Again, all those things are on your formula sheet if you forget. Alright, this next one, we have a quadratic that's already factored, so that's beautiful. Sign charts work really nicely here because we're going to be giving domain, and your two x-intercepts, critical points, would be at -5 and positive 1/2. So if you were to either graph or test some points, you'd find out that before -5 the function was positive, and then negative, and then positive. So the question is, where is your function greater than or equal to 0? So that means positive. So they're looking here and they're looking here. But also I want you to recognize that they're using an equal to 0 symbol as well. So we're going to have to use brackets here and here when we get to the interval notation. So it starts at negative infinity and then, oh geez, that's ugly, and then goes to -5 with a bracket. And then union picks up again at 1/2 with a bracket, and then goes to infinity. For the rest of the domain it's positive. Wow, that is ugly handwriting. Let's try that again. You know, I kind of forgot to mark that that was on part 1. The good news is it totally was on part 1. So, this is part 1. This is part 1. And this is part 1. Alright. So then, 18 and 19, oh, what just happened there? Oh, it was again. Alright, so 18, 19, and 20. These are all going to be part 2. So we're going to hold off on these for another video. Okay. 21 is also part 2, and so is 22. And so is 23. So look forward to those on your next video. Alright, finally, 24. We get back to a part 1 question. So, turns out everything for the remainder of the page here, all the matrices stuff, and the rest of the systems, this is all on part 1. So, you can kind of stop marking if you just write at the top of the next page, part 1, the whole thing. So the first question talks to you about the dimensions of a matrix and whether it's possible to multiply two matrices together. So the first matrix is a 4 by 5. And you're multiplying that by another matrix, which is 5 by 1. And the rule for multiplying matrices together is if their inside dimensions match, then it's okay to multiply them together. And then the resulting matrix would be the dimensions of the outer ones. So first answer is yes, it's okay to multiply them. And the second answer is the resulting matrix will be a 4 by 1. And remember, multiplying these by hand, it's super important that you have the appropriate dimensions written down kind of as a skeletal answer, because these can get kind of weird. All right, this is a advanced substitution question, and you want to solve for the easiest variable that you think would be to solve for, and I'm going to solve for x, because I'm looking, and I'm thinking this x would be so easy to get isolated. So, x equals, we're going to add the y over, so y plus 6, which means anytime I see an x, I'm going to use an y plus 6. So right away, we have x squared plus 2y squared equals 27. And we don't typically have a situation where we're solving for y, but it does work. You just have to be careful that you're writing them down in the right part of your answer. So y plus 6 quantity squared would be y squared, FOIL this out, plus 12x, or 12y, plus 36. And then we still have a plus 2y squared, and then equals 27. So you definitely have a quadratic. We got to bring everything to one side to get it in standard form and make it as simple as possible. So combining those y squareds together, you get 3y squared. And then, let's see, I have a 12y. And then you're going to have to subtract the 27 over and combine it with the 36. So that gives you a minus 9. So solving this quadratic, ooh, you know what? We can divide everything by a 3. Let's make it even easier on us. So, new quadratic, y squared plus 4y minus 3. I screwed up somewhere. Alright, what did I do? 2y squared, 3y squared. Alright, hold on, I'm going to look at it. Ugh, so dumb today. That's a plus 9. That's a plus 3. Alright, that's better. Equals 0. So you have y plus 1 times y plus 3. So we're finding two possibilities for y. So your answers, remember, are ordered pairs. But be careful, usually we have x first, this time we have y first. So -1 could be y, and -3 could be y. So now you gotta go back. The good news is you have a nice recipe for x. X is known as y plus 6 in this problem, right? So if you just go back and plug in your y for plus 6, let's see, that gives you a 5. And then plugging in -3 plus 6, that gives you a 3. So it's very important that you go and find all possible solutions, because these typically have 2, and I think on your test it's exactly like that. Alright, so now there's another matrix question. We have inventory, plus we get a new shipment. So you're supposed to figure out what operation to perform on these. Well, we're adding them together into our inventory, so we're adding these together. So the updated matrix is going to have the same dimensions, and you just got to add everything up. So 11 plus 100 is 111. 113 plus 0 is 113. And then 87 plus 44 is 131, I think. And then 0 plus 177 is 177. So you don't have to do anything with that matrix other than just compute it. Alright, so next matrix operation says that we are supposed to figure out what scalar to use on the scalar multiple and then update the pricing matrix. So they want to mark up all their prices by 12%. So that means they want to take all of the percentages, all of the price that's already there, and add an additional 12%, which means you're going to take 100% plus 12%. So the scalar has to represent 112%. So think about what decimal that would be. That would be 1.12. And that's what you're going to multiply all these by. Now, there's nothing wrong with not using a matrix on your calculator. You could just manually multiply each one of these by 1.12. You just have to make sure that you're understanding that this is a pricing matrix, so you need to round appropriately, which means to the 100th place if you need to round at all. So like this first one comes out to 3.67 when you round, and this one comes out to 5.6 or 5.60, and then 1.67, and then 10.07. $10.07. Okay, so just watch the rounding on this one, because you have to make sure it makes sense for the problem. Matrices are all about applications. Alright, more matrices. You want to just set it up as a row reduced echelon form looking matrix, so something that you could type in your calculator. And you can do a 3x4. So coefficients, just be careful here. You got a 1, a -5, a -1, a 2, and a -11. And then you got a 4, a 2, and then you have nothing in the z part, -3. They should be relative. No, that's a typo. I think this is supposed to say W. Sorry, I don't think I fixed it on your page. And then 17. That was my bad. There's nothing tricky like that. It wasn't meant to be tricky. Alright, 2, and then there's no Y. There's a -4, and then a 1, and a -6. And then a 1, a 7, a -1. There's no W, and then a 6. If you want to put like a dash line here to separate the solutions part, you can. I'm going to hurry up and fix my typo on here. Whoopsies. Alright, so again, that was not meant to be tricky, guys. Just set it up. Now this one I want it set up as an augmented matrix, and then you're going to go solve. So your coefficients for just the body of the system, so just this part, are 1, 3, -1, 3, -1 and 1, 4, 1, and -2. And then your variable matrix goes in order again, so first x, then y, then z. And then equals the solutions matrix, which again goes in order, so 10, 8, and 23. And then we're hoping that you guys understand. Technically, you can go back and enter it as a 3x4 and do row reduced echelon form, but at the very least, we need you to know how to break it up into this augmented matrix. What you need to do, technically, we're hoping you'll do, is call this matrix A. And this is just a variable matrix, and call this matrix B. This is a 3x3, and this is a 3x1. And then you're supposed to do A inverse times B, because remember, you can't divide by a matrix, but you can apply the inverse matrix in order to undo it or to move it across the equation, if you want to think of it that way. Either way, you get a solution, an ordered triple of x, y, and z of 4, 1, and -3. I'm not showing how to enter matrices on this video because it's kind of laborious and not enough time. So if you need a little help on how to enter matrices, you're going to have to go back and watch that video for that lesson. Alright, this is a special case of matrix solution. So you've done the row reduced echelon form, and it turns out that you have a weird solution. And the reason I can tell it's a weird solution is because of this guy right here. Because 0 does equal 0, it's not a no solution. There is a solution. The problem is there's too many solutions. So this is a case where there's many solutions. And remember what it looks like when there's one solution. You get, like, for the last variable, it'll be the identity. It'll be the identity matrix over here. But when it's no solutions, you get something like 0, 0, 0, and then like a 4. You know, on that side, where 0 can't equal 4, and that's a no solution option. So watch out for that. I think on your test I asked you about all 3, so just be super careful. So that's not that problem. Alright, but let's talk about what our solution could be written as. So many solutions. The goal is that you're going to still give me a solution as an ordered triple. The problem is your ordered triple is going to be funky. So what I do is I take my first row and I write out what it represents. So this represents, let's use x, y, and z. 1x plus 4z's equals -9. And you can solve for x by subtracting the 4z over. So you get -4z minus 9. That's what I'm going to use in place of x. And then your middle equation says 1y plus 7z equals 3. So I could solve that equation for y by just subtracting the 7z over. And I'm going to use that for y. And the reason we can get away with that is because we're just going to let z equal z. So if I gave any number for z, I could plug it into all three parts of the ordered triple and get one solution. It won't be a unique solution to the system, but it will be a solution. One of many, unfortunately. Oh, I feel like we need a breather after that. That was your part 1 video. All right, good luck. Part 2 video is totally separate. Oops.